So, okay, okay, thank you.
Sorry about that. Thank you for that. So when we're looking at a sample and we're looking at a statistic as opposed to a parameter, right? And we're trying to determine what's taking place. And we want to measure things. And we're trying to figure out, okay, how many people have flu-like temperatures or flu-like symptoms? Like, are they sick or not sick, breathing, having problems breathing? If we look at a database, those are names: breathing or having problems breathing, not. As opposed to, what's your temperature? Oh, the temperature is 108. Oh, it's 105. Oh, it's 102. Those are different. And because they are different types of data, we need to have different tests to measure those. If we're looking at, like, okay, they're having problems breathing, they're not. They have nausea, they don't. That's categorical data. With categorical data, there's a couple tests we can use. A z-test, chi-square. Temperature, how long it takes them when they're in the hospital, that's numerical data. With that, we measure like means or averages. That's our t-test and our ANOVA. Okay, so I just want to make sure that we're clear between those and why we use those with the different types of data. Now, moving past this of the basics and past the point of the different types of data and the different types of tests that we use, we then get into the area of where we have descriptive statistics and inferential. Okay, so descriptive statistics, when we take a look at that, that is just simple, like central tendency, variability, and the shape of the data. So when we start looking at perhaps somebody that has COVID, and we look at the descriptive statistics, and we're looking at, oh, what's the average hospital stay that they have? We can look at the mean, we can look at the median, we can look at the mode, and it would tell us how long on average are these people staying in the hospital. We could have some outliers that, you know, they have maybe some underlying conditions, so they stay way longer than other people. Or we could have some people that are very healthy and they kind of just stay a couple days and they're in and out, right? And so those outliers can affect our data. So perhaps if we have outliers, we want to use the mean as the median as opposed to the mean. Okay, but if we have a sample size greater than 30, then we can just run with the mean because of the central limit theorem. Okay, so whenever you're doing these studies, it's always advantageous to have a sample size of 30 or greater. So the descriptive statistics could give us central tendency, mean, median, and mode. Also variability, like on average, how much do they differ from that mean? The standard deviation, so the mean is 6 days on average, how much do they differ from that? Oh, 2 days. Coefficient of variation, oh, it goes up or down about 10%. IQR, the interquartile range. On average, the middle 50% of the people are staying in there anywhere from 5 days to 8 days. IQR. Now, we can also look at the shape of the data. Now, the shape of the data tells us a lot. If we're viewing some people that are sick, we want to find out what are the normal conditions and what are the normal symptoms for them. So we want to make sure that our data is normal. So when somebody asks, we can say, no, this is normal. And so in order to have that normality and is to establish what's normal with this COVID, we can look at the data. And when we start looking at the skewness and the kurtosis, the skewness and the kurtosis, when we look at the skewness, we're going to measure the mean against the median. And if we notice that there's a huge difference, there's something wrong here. The mean and the median should line up. If the median is much higher than the mean, or the mean is much higher than the median, then it tells us that there's something wrong with this data, right? They should be close to the same. And that's what tells us with our kurtosis. Okay, so we're looking at the mean. If we have a median that's 2 higher, then we're going to have a +2. If we have a median that is 2 lower from the mean, we're going to have a -2. And that tells us something's wrong. They're not lining up. Our data is not normal, or maybe our sample size is too small, but our data is not normal. There's something wrong with it, right? This virus isn't acting normally. Okay, we can also look at our kurtosis. Is it peaked or is it flat? What does that tell us? Do we have a lot of data in the center, or do we have a lot of data kind of spread out? So far, so good? Hey, Jay, I'm doing boot camp. Can I call you a little bit later?
Oh, sure.
Okay, all right, thanks. Bye-bye. Is it peaked or is it spread out? So now going back to variability, because we need to cover this because this is key. And we did this early on, and I want to do this again because this is actually going to bring back a lot of good and bad memories, I guess. So I'm going to calculate out a standard deviation. Okay, so we're just going to focus right now because I'm going to go along with the same idea about the average amount of time that somebody spends in the hospital for COVID. I'm just going to use that example. And so imagine we do this sample and we have somebody that stays 7 days, 5 days, 8 days, 4 days, 9 days, 3. Then all of a sudden we add that up and we have 36 days. Can you guys see all the 36? Yes or no? Because I have something in the way of mine. Yeah?
Yeah.
I'm going to turn down these lights for you guys if I can figure out how to do that. Anybody see a light switch?
No, I'm sure.
Back here. I'm just not seeing a light switch. I apologize. There's just nothing up here. Now that I've got my notes. Okay, sorry about that. Okay, so we have 36. When we total all the days of all the people, it's 36. Now we have 6 people in our group. So when we divide that by 6, we have an average of 6 days. The average person is spending 6 days. Do we see that? I'm going to pin this just so we can all see it. Okay, so we have an average of 6 days. Did anybody stay 6 days? No, we have a problem here, right? We're saying the average is 6, but we're saying, hey, wait a minute, nobody stayed 6 days. What's going on here? So we want to figure out what's the average amount that they differed from the average. That's a standard deviation. So we're like, okay, well, the average was 6. So let's just subtract that and see if we could find out the average amount that they did. +1, -1, +2, -2, +3, -3. When we do that, we get a 0 and we're like, hey, wait a minute, this is not working. So the way that we fix this is we have to square the data. And so how do we square the data? That's 1, 1, 4, 4, 9, 9. Okay, so we have to square the data in order to move forward with this process. And so when we add all this up, that's 28. What I'm going to do is we're going to use this later on. I'm going to call this a sum of squares. we're going to actually use this when we get to ANOVA, right? We're going to use this when we get to ANOVA. Also regression, right? So it's key, so we have to know that. Okay, so the sum of squares, so 28. Okay, so can I divide 28 by our sample size of 6? I want to, but what I'm going to do is I'm going to remove one. And when I remove one, it's called a degree of freedom. Okay, we're going to use this when it comes to ANOVA and regression again. I'm going to call that a degree of freedom. So why do we do a degree of freedom? It's supposed to add randomization to our data. So it's supposed to add randomization to our data. Why is that important? Because we figure out for ANOVA, we need our data to be random. We also need that for regression, the t-test. So what this is supposed to do by removing one is add randomization to our data. And it's also supposed to fix some issues just in case we have calculation issues for whatever reason. Okay, not calculation issues, but some issues with the data variability. So it just fixes that. So when we divide 28 by 5, we get, what's that number, 5.666 or something? If memory serves me correct.
Yeah.
5.6. That number of 5.6, does anybody remember what that is? Huh? No, what's the one right before standard deviation? The variant. The variant. We use this too in ANOVA because one of the calculations in the ANOVA is a variant. And so what happens is we take this variant and we square the data back here. So we need to square root that 5.6. And when we square root it, we get our standard deviation. So then our standard deviation is, I think it's 2.23 or 2.3333, something like that.
Yeah, 2.36.
2.36. Okay, and so that's our standard deviation. And so all these things in it that we learned during this calculation, we're going to use later on with our ANOVA, with our t-test, those things. Okay, so I just kind of wanted to bring that back into our memory. And so now when we look at something like that, with that mean and our standard deviation, we can start to plot this out to see what it looks like. I'm going to plot this out in a normal bell-shaped curve, right? I'm going to plot it out with a normal bell-shaped curve. And so right in the middle, 50% on this side, 50% on that side. I'm going to put our mean. And I'm going to say our mean, our median, and our mode all line up. Perfect bell-shaped curve. Skewness and kurtosis both 0. Okay. And we found out with our data, the average person stayed 6 days. I'm going to do some country math. So I'm going to round off the standard deviation instead of 2.36 just to 2. Just so it makes it easier for all our calculations later on. So one standard deviation above the mean is 2. So 6 plus 2 is 8. One more standard deviation above the mean, 8 plus 2 is 10, and 10 plus 2 is 12. One standard deviation below the mean, 6 minus 2 is 4. 4 minus 2 is 2. 2 minus 2 is 0. That's my mean. That's my standard deviation. This is within a bell-shaped curve. Okay. Now, with the bell-shaped curve, in order for it to have a bell shape, we notice that we need to have a certain amount of data between 4 to 6, 6 to 8, 8 to 10, 10 to 12. And we notice that there's less data in each one of these, I'm going to call it bars, but in reality, it's a histogram, but I'm just going to call it within each bar. Okay, just to make things simple. So we notice right here that we need to have about 34% in each one to have that high point. This just normally happens. In here, we have 13%. And out here, we have about 2%. Okay, and that's to have the normal bell-shaped curve. And so when we're looking at our data, we know about 34% of the people that have COVID stay anywhere from 6 to 8 days, 13% from 8 to 10, and 2% from 10 to 12. 34% from 4 to 6, 13% from 2 to 4, and 2% from 0 days to 2 days. Okay, that's our normal bell-shaped curve. And this is how things normally happen within this disease, as long as our skewness and kurtosis is between -1 to 1. Okay. Now, based on this bell-shaped curve, if we wanted to figure out what percentage of people stayed at certain days, what we could do is we can add percentages to this, 0%, 100%. And we can use this cumulatively to figure things out. Okay, we can also add in probabilities. And the way that we would do this is in calculus, you learn something for solving the area under the curve. And in the curve, as long as we know how much should be in here, we would say, what's the probability somebody stayed from 0 to 2 days? Oh, about 2%. The probability that somebody stayed from 4 days or less, 13 plus 2, 15%. So what we've done is we've made sure that each one of these standard deviation lines are marked in the same intervals. One's not bigger than the other, one's not smaller than the other. No, they're all within the same intervals, right? They're all about the same size. And based off of that, we've also tied in smaller. You can break these standard deviations into 1.5, right? 1.25, 1.26, 1.35. So there's all kinds of numbers inside this. So this is continuous, not discrete. Not just 1, 2, 3, 4, 5. No, they have like infinite numbers in between every single one of these. Okay. And so instead of every single time us using calculus to solve for the area under the curve, what somebody did was they figured, hey, if we're going to tie this to standard deviations, why don't I just figure out how many standard deviations and what that actually means? And so what they've done is they've tied standard deviations to these, or sorry, they've attached probabilities to these standard deviations, and they've put it in a chart. And if you tell them how many standard deviations either above or below the mean, they'll tell you what the probability of being at that point is. Okay. And right here at the mean is 50% on this side, 50% on this side. And as we go up, it goes from 0 to 100%. Okay. And we're looking at this cumulatively. So cumulatively means from whatever point down. Okay. From whatever point we're looking at down. And so as long as we know our standard deviation, because we look at standard deviations here and say, oh, if somebody was there like, 1.6 standard deviations above, it would be 94% of that or less. And how do we get like 1.2? How do we get that number? How do we actually get that number of how many standard deviations above or below? So we actually use something called a z-score. So as long as we know our standard deviation and our mean, we can solve and get a z-score, and from that z-score, get a probability. Okay. So if somebody were to ask, what's the probability somebody would stay 10 days or less? Oh, you can solve for 10. 4 over 2, that's 2 standard deviations. We look at 2 standard deviations. and it tells us about 97%. About 97% of people spend 10 days or less. 3% of people stay more than that. 97% of people stay 10 days or less. 3% stays more than 3 days. That 3% we call the alpha, and in just a little minute, we're going to be calling it a p-value, the probability of being right at that point. Okay. So what I did was I solved for 10 days. So 10 minus 6 gives me 4 over 2, and that's 2 standard deviations. And if I look right above that, I can see that 10 days is 2 standard deviations too as well. So I use the z-score, and then it tells me that it is 97% probability from that point or below. I can also figure, hey, what's the probability somebody would stay like 2 days or less? 2 minus 6 over 2 gives me a -4 over 2, a -2 standard deviations below the mean, right? And if I solve for that, and that told us that it was 3% down here and 3% up there, we can also solve for the area in the center. I rounded this off, it's really 2.5, and this is 2.5. And if we have 2.5 above that line and 2.5 below that line, right here in the middle, it's 5% on the outside. Right here in the middle, we would have 95%. That 95%, what we could call that is we can say, I am 95% confident that the average stay in a hospital for somebody with COVID is anywhere from 2 to 10 days. And that's known as how confident you are based off of a range of numbers, an interval. So it's called a confidence interval. We use this confidence interval to estimate what a parameter is based off of a sample and a statistic, which is a great tool. We don't have to measure everybody. We can just do a sample of 30 people in whatever country and figure out why people are getting sick. We don't need everybody, which allows us to operate really quickly. We don't have to start looking at 100,000 people trying to figure it out. No, we can operate very quickly. We have a small sample. The sample is representative of the entire population. We're pretty good. So instead of us measuring everybody and say the average is 6 days in the hospital, no, we do a confidence interval. We say anywhere from 2 to 10. And so if we measure the entire parameter, we'd say anyone that stays more than 6 days is more than average. Anyone that stays less than 6 days is less than average, but average is 6. But we already know that 6 isn't accurate, especially with our sample, because everybody didn't stay 6. Everybody didn't stay 6 days. So we had 7, 5, 8, 4, 9, 3. They were all different amount of times. And so if we treat that confidence interval as anybody within here is considered the same and just normal variation, anything outside of this is longer than average up here or below average down there. So what we treat it's anything above 6 above average, anything below 2 days is below average, or above 10 days is above average. That's how we treat that. And what we're able to say, if we have a 95% confidence interval, is that we are 95% confident that we captured the parameter within this interval. Okay. And the reason why we treat it as the same in normal variation, when we actually look at our sample, all these data points fall within that. So within our sample, all those data points were normal to be within 2 to 10. We had people stay 3 days, 4 days, 8 days, 5 days, 7 days, 9 days, right? Those are all completely normal. And that's all within our sample. Okay, so our confidence interval, it allows us to estimate what the parameter is based off of a sample. Okay, and we treat it as if it's a parameter, but we don't treat it as a single number, we treat it as a range. So far, so good. This is kind of key to understanding where we're going, right? That we understand this, because we're going to jump into t-tests here really quick, okay? But what I need to do is to find out if I need to explain this just a little bit more to people, okay? So I'm just going to do real quick, give me the heads up. Tim, are we okay with where we're at? Maria, okay? Okay, how about you, Justin? Okay, Alyssa and Alan, we good? Jessica, Kobe's good, Chica, and Carson, and how about you, Haley? Are we good?
Good.
Okay. And if you guys have questions along the way, please ask. I just want to make sure that we are all on the same page. Okay. So now that we can take data that's not quite so predictable, and this is where we need to wrap our head around, is that when we have data that's not the same, if we had, every time people come to the hospital, that person takes 6 days, 6 days, 6 days, 5 days, 5.9, 6.1, it's easy. But when you have these huge shifts where it's kind of all over the place, how do you make sense of that? That's where it becomes a problem. It's when the days are just kind of all over the place. Someone stays 3 days, somebody stays 9 days. Like, how do you make sense of that? If it was close to being the same, we wouldn't need any of this stuff. But because we have such huge shifts, we need to measure it. We need to be able to have a system in order to take care of that. Okay. So now imagine if we wanted to take a look at hospitals to find out if certain care was actually allowing people to heal much quicker. Imagine if we want to see, okay, well, wait a minute, these people are going to the hospital. Well, let's put them on respirators. Does that help? We could measure that because now we know what the average stay is. Does it give them a quicker, where they get out of here like quicker? Does it help them? We could begin to test that. And when we test it, we need to be able to communicate this to other people so they can understand it. So if we want to say, okay, the average stay, okay, so how do we determine how we write average stay? Do we just go like this? Average of people that aren't on the respirator equals the average. Do we do that? And what's average? Is it the mean? Is it the median? Is it the mode? I mean, what are we measuring? We want to make sure that we're all on the same page so we can follow the same thing. So like, okay, well, let's create a symbol for that. And so we're going to use this symbol for the mean. Okay, we're going to use that symbol for the mean. And so we can then say, hey, the average, and I'm going to number these just so we don't forget. The people without the treatment and the people with the treatment. Both of them are going to stay the same amount of time. And our alternative is going to say, no, they're not going to stay the same amount of time because we think the treatment is going to allow them to heal much quicker. So they're going to get out of the hospital much quicker. And they're like, okay, well, how do we know if one of them is different? Because this data is all over the place. Okay, so what we could do is to create a confidence interval and treat this as the same. And we know that the people that are sick, this one, on average, they're saying six days, but we know that not everybody stays 6 days. Hell, some people stay 3 days, 9 days, 4 days, 8 days, 5 days, this. But we have this confidence interval that goes from 2 to 10. okay? But the group, the mean of the group is what we're looking at. We know that there's variability within the group, but the average of the group is 6 days. And so we know that this is 6 days. And so now we want to test to see if this is lower, if this is on this side. Is it lower than 6 days? We can test that. And so what we want to test is, okay, without treatment, we're putting these people on respirators. Okay, are they going to get out quicker because they're having breathing problems? Or perhaps we're giving them some type of medication in their lungs to help it heal a little bit quicker, make them breathe a little bit better, right? Remove phlegm or something. So we want to test that. And if we want to test 2 variables, we use a very old test called a t-test. And it allows us to test 2 means. We can't test more than 2 means. We couldn't test like average people, people that were putting on a respirator, people that were giving lung treatments, people that were getting antibiotics. We can't do that because a t-test is only 2 variables. If we want to test more than that, we would use something called an ANOVA. Okay. The t-test is a very old test that only tests the mean between 2. And all we're looking to see if one of these means is higher and lower than the other one. And when I say higher or lower, I'm saying statistically higher or lower, and higher or lower is either lower than 2 or higher than 10, not higher than 6. Okay. So with my t-test, I can then go in and if I create a confidence interval, and it's 2 and 10, and I have 1 in here that's at 6, and I'm hypothesizing that this will help. So equal as if both of them are in here, and not equal, this one is in, one's in here, either one's in here or one's in there. Yes.
So your hypothesis, your null hypothesis stating that if you use this treatment, it's not going to make any difference from the average.
That's it. Yeah, it does nothing.
Yeah.
We could see some variability where they go from 6 days to 3 days, but that's not significantly different. And people stay in there 3 days, 4 days, right? We had that. We get that. In order to be significantly different, it has to be less than 2 days, right? Because we've just estimated that the parameter based off of these 30 people that we're testing, that the parameter is between that. And so that's what we're doing. What we want to see is 1 out here and 1 there, and that tells us if it's actually working. So the way that we do this in academics is we use something called the probability value. Because not everybody, when they get the treatment, is going to be less days, even if they're different. But we can tell the likelihood or the probability that they will get treated or that it will work, right? The likelihood that an event will take place in the future if we give them this treatment or this medication. We're not saying 100%, no, because not everybody, but the likelihood of most people, because we can't prove things 100%. No, everybody's slightly different. Some people may react to it really well, other people like not so well. Okay, so that's what we're going to test, and we're going to give the probability that they will get better based off of this treatment, based off of this, and that's what we're looking at. Okay, so we're going to calculate our probability, and we're also going to calculate significance, right? Because we need to compare what our person did or our group did based off of this confidence interval. So our significance is telling us what these people are doing, and we need to make sure that what our people are doing or this other group is actually different. So our significance level, right? So anything in here is completely the same. The amount that's significantly different. So 95% is the same. So we want to make sure that our people are different, right? So what level would make them significantly different? At what level would they be significantly different? That's what we're asking. At 5%. If they're 5%, at 5% would be significantly different. But in this case, we're looking at 2.5% up here, 2.5% there, because we don't know if this treatment's going to make them worse or better, because we need to test both of them at first. We can give them a treatment and it could actually backfire and say, okay, we found out how not to treat them. But the amount that would tell us if it's significantly different is 5%. So we need our probability to be close to that range to show us that it's significantly different. Okay, anything that's the same as in here, anything that's outside here is significantly different. 2.5% and 2.5% is how we get our significantly different. 95% the same. If the value is 100% and 95 is the same, 5% is different. Okay, this is our confidence interval. What we're hoping is that it's down here, that we give them the treatment and that it's less days. That's what we want to see. We don't want to see up here. So imagine we give them the treatment and we find out that they stay 1 day. We know that our mean is 6 and our standard deviation is 2. That's 5 over 2, which gives me what? A negative 2.5 standard deviations below the mean. So when I look at a negative 2.5, do we see that number? 0.006. That's my probability. If it's a negative number, the number on here is a probability. If it's a positive number, you need to use the alpha. Okay, so it's giving me a probability of 0.006. So now that the people are staying 1 day, my probability is that, my level of significance is that, if my probability value or my p-value is below my level of significance, I can reject my null hypothesis. So this allows me to reject my null. Oh, they're not the same. But now I need to address this too. I can't just reject that. I need to address that. Okay, so they're not the same. What now? Now I can say I am 99.4% confident that people that get our treatment will stay less time. 99.4%. How'd I get that number? I'm not 95% confident. My actual confidence is 99.4. So if I have 100 and it's not actually, yeah, 100 minus 0.006, right? That's my confidence. Okay. Now that I'm able to say like, well, hey, this treatment appears to be working. And if somebody gets this treatment, they have roughly a 99% probability of, getting out of the hospital really quick. Not everybody, no. Somebody said, hey, somebody didn't get out. No, I get it. 99%. 1% of the people, it ain't gonna work for. That's how that works. Not everybody. You can't prove this 100%. There's no way.
Sorry,
Okay,
Professor.
Sorry, go ahead.
So we are 99.4% confident that less than 2 people are gonna stay in hospital, or more than 10,
No.
or just like.
Yeah, so that it's different, right? But because our number's below, we would say that we're 99% confident that they would stay. But
Why?
essentially, you're right. It would be different than this. And that's how confident we are that it's different than that. But because our number is below, we can then say like that they would actually stay below. But you're
And I'm
essentially
below
right,
what?
yes.
What do you mean?
So the same is in here, different is out here. So essentially, theoretically, you're right that we're 99.4% confident that they would stay outside of 2 to 10 days. You're right. But because our number was below this, we would just say like, we're 99% confident that it appears that they're going to stay on the lower side. Does that make sense to you? Just because our data backs it up.
Okay.
But if it makes more sense to you just to say it's outside of those, go with that.
Okay. Okay.
Because we could do an upper and lower tail test too here. Are you with me, Tim?
Yeah.
Okay.
Yeah.
So we could do an upper or lower tail test as well. Okay. But what we're going to say is based off of our data, we're 99% confident based off of that they actually stayed 1 day, that it should be that.
Okay.
Okay. Now what we need to do is somebody's going to say, well, how sure are you of your results?
Chris,
Yes.
I have a question.
Bring it.
So it's kind of like regarding what Tim said. So basically, we just did the lower test because it's like, is that how you got the number 1 when you said 1 minus 6/2? Because you chose a point below
That's
2.
it. That's
Okay,
it.
okay. Just
So we
checking.
chose 1 day, right? So we chose that they're going to stay 1 day, and then we got our probability from them staying 1 day. And the probability of this happening was that.
Okay,
And
cool.
so then we can say how confident we are that it would be 1 day.
Okay.
And that's the reason why I said that, Tim, is because I chose 1 day.
Okay. Thank you.
Kind of backs up our data. And so imagine somebody would say like, well, how sure are you of this, man? Because there's a lot of people getting sick. Like, is this pretty accurate? Because this is like cutting edge. Like maybe it's a new treatment that we have. Hey, wait a minute. The first thing that you need to do is to hit them with antibiotics. And with antibiotics, maybe that's what that is, or maybe that's a breathing machine, but whatever it is that we say that we're doing that's fixing this, we need to make sure that this data is accurate and it's not just something that just happened by accident. And so how do we prove, because we're using a p-value to reject a null, how do we prove that this p-value is accurate? And that's for a t-test. And what we need to do is we need to make sure the data is normally distributed. Why? That's one of the assumptions. It's going to be the assumption for the t-test, the assumption for ANOVA, and the assumption for regression. All of them are going to be like, is your p-value accurate? Because we're using a p-value to reject this null hypothesis. And how do we check the accuracy of the p-value? Now remember, our p-value is based off of the probabilities that somebody has designed within this normal bell-shaped curve. And so they've attached it. So one of the assumptions is that this normal bell-shaped curve is normal. If skewness and kurtosis is off, then area under the curve is going to be all screwed up. Here's one way to see that. Okay. So we know from 0 to 2 days is roughly about 2%. From 2 to 4 days is about 13%. 4 days or less is roughly 15%, sorry. We can see those percentages because this thing is built like that. And we're assuming that as long as the data is normal, that those probabilities are okay. So what would happen if that was, instead of 34, if it was 47, 36, 13, and 2. Before we said the probability that somebody would stay less than 4 days was 15%. But if this data is skewed to the right, we are missing this part of the data. And because our data is not normally distributed, instead of saying, hey, the average person, the probability they stay 4 days or less is 15%, we look at it, the average they'd stay 4 days or less, there is none. And so our probabilities are off if our data is not normally distributed. And that's why we always look at our p-value, and we always check the accuracy of the p-value with the shape of the data. How far off is off? Again, when we look at our skewness and kurtosis, if it's between like, I think all the way up to like maybe 7 or 8 or 9, it's off by less than 1%. Right? So we can have some pretty high skewness and kurtosis as long as our p-value is low enough. It doesn't really affect it that much, but it does affect it. Okay. So far, so good. So now that we've ran this test, we need to check the accuracy of the p-value. That's one of the assumptions. That is normally distributed. That way the p-value is accurate. And if our skewness and kurtosis is between either -1 to 1 or our sample size is greater than 30, then we can say this test is okay. And then you're like, okay, well, this test is okay. I get it. We can now test if breathing machines actually gets somebody released from the hospital early. Well, that's nice, but how about, isn't there other stuff that we can do too? Is it only a breathing machine? How about if we wanted to test like more things like this? If we then wanted to say, we want to test the average person against somebody that's on a breathing machine, against somebody that's taking antibiotics, against somebody that's on this isolation, against somebody that's doing isolation, breathing machine, and antibiotics. I mean, we can even combine those, but we're trying to figure out what is the best mix for us to treat these people. And we're going to say like, hey, all of them are going to stay about the same amount of time. Our alternative is going to say, no, at least one of these average stays or the mean stays is not going to be equal.
You remember what test this is? This is
The ANOVA.
right?
So anytime we're testing more than 2, it's ANOVA, analysis of variance. And so we're then going to test that. Why is this ANOVA important and why am I spending time on it? Because the ANOVA is the key to the regression. It's the main part of the regression. So we're looking at this. We're going to make sure that we spend good time on it. And with the ANOVA, the assumptions are independence, normality, equal variances. There's only one more assumption for regression, and that's linearity, right? So bulk of understanding regression comes from this. Okay, so I'm going to make sure I do it justice so we understand. So the ANOVA, when we're done with the test, we're going to do the same thing if we're 95% confident that we've captured the parameter. 5% of the data is different, 2.5, 2.5. Anything in here is the same. Anything outside statistically significantly different. We can then begin to check things to see, hey, is one of these different than the rest? Is one of them going to be less time, more time? I mean, what does this do? And perhaps we can even test more things as well. And so we begin to test. And what we're hoping is that one of these treatments is going to make people stay significantly less. So if we know our confidence interval, we can know what would make it, this medication, significant, what level it would have to be, or what's that critical value. Now, what we would do is compare our p-value to that. And if our p-value is below our level of significance, we can reject our null. and it would tell us how confident we are in the alternative. Right? And so we're doing the same thing that we did for the t-test when we're evaluating this. And we're going to do the same thing in regression. We're going to do the same thing in the z-test and the same thing in chi-square. If our p-value is below our level of significance, we're going to reject our null hypothesis in all the tests. We're not reinventing the wheel for any of them. Just want to make sure that we're okay with that, that we understand that.
Sorry, Professor.
Sure.
Isn't like just be like below significance level 0.5 and you can already reject the null hypothesis?
Yes, if our p-value is below that.
If the p-value is below 0.5.
Then we
But
can
with
reject.
regression, like we look at the significant f and then see if it's below 0.5, right?
So you're talking about in regression.
Yeah.
Okay, yes. But I'll get to regression later on, but significant F is the p-value. So the ANOVA is also called the F-test. And the reason why it's called the F-test is because the guy that designed it, his last name is Fisher. And that's why they call it significant F instead of p-value, just to kind of give them a little bit of credit. But it is the p-value. It is the probability value. Okay. Sometimes they used to call it the F ratio, significant F. That name has changed over the years, but essentially all of them are p-values, probability or likelihood of this happening by chance alone. Fisher, the guy's name.
You said
Oh, analysis of variance. Is that what you're looking? So analysis of variance, how much something differs from the rest. We're trying to analyze that. So far, so good?
that doesn't tell us exactly which one. So that means it's two.
Yes, give me just a second. So now if our p-value, so I'm just going to invent this p-value. I'm going to use the same one that we did for the t-test, 0.006. And we can reject our null and say that we're 99.4% confident, 99.4% confident that at least one of these are different. Is it one that's higher or is it one that's lower? I don't know. But what happens is that the ANOVA doesn't tell us which one's different. All it tells us is one of them's different. That's it. That's it. And that's similar to what the t-test does. Hey, one of them is different. But with the ANOVA, they've then attached something that's called a post hoc test. That's called the Tukey-Kramer. And then the Tukey-Kramer then tells us which one is different. The Tukey-Kramer is essentially a t-test between all the variables to see which one's different. Hey, is this one different than that one? Is this one different than that one? That's all it's doing. So then it'll compare all of these. They used to call it the pairwise test against each other to see which one's different. Hey, is one different than two? Is two different than four? Is two different than three? Is one different than six? And it's going to kind of compare these to see which ones are significantly different than the rest. That will be our Tukey-Kramer. We'll get into that in just a second. So the ANOVA only tells us one of them is different. Hence, now we have to have another test. And in regression, the ANOVA only tells us that the slopes are different only. We need to have all these other assumptions and all these other ways of finding out which one's different, how much is it different, by what amounts, and hence we need all these other tools. So far, so good. Now, after we run this ANOVA, we're like, well, how do you know that one of them's different? How do you know that this test is accurate? It's valid. So with the t-test, we just simply looked at normality because we needed to check our p-values because we're using a p-value. So how do we know that's accurate? The way we know that's accurate is we look at normality. What is normality? we look at skewness and kurtosis. And if skewness and kurtosis is between -1 to 1, then that means that it's normal. If it's normal, because this is a normal bell-shaped curve, then we know that our p-value is accurate. Now, if our sample size is greater than 30, the central limit theorem tells us that we can assume that it's normal without checking it. But if it's less than 30, we need to check skewness and kurtosis. Okay, which is one thing. So we also need to check independence and equal variances. And why? We need to make sure that we're measuring each one of these independently from each other and that they're not all tied together somehow, so the numbers are convoluted.
What variable is this again? That last.
So when we're checking them, we need to make sure that we're independently checking them and we're not mixing all the data together and it's not overlapping.
That's
Right.
what's repeating.
No, so our independence, we need to make sure of that, to make sure that each one of these are being independently checked and that we're not having any biases or we're not combining stuff together. Now, the easiest way that I can get you to understand what dependency does, or when you're measuring two things the same and you're kind of mixing them together and the data is not really valid when things are too dependent, when you're really measuring them together, the easiest way to get you to understand that is I'm going to use this example of a car and brakes to see how when things are too dependent and you're measuring things together, how it could create some error in the model. So imagine we have a car and we're trying to figure out which is the best brake pad. So we have 4 tires and we have 4 brake pads. So one is going to be Bosch, one's going to be Tokiko, one's going to be Delco, and the other the Walmart brand. And we just randomly put one of these brakes on each tire, right? So imagine we are just testing all these people together and we don't have independent groups testing them. It's the same group and they're measuring the same thing and it's too dependent. We're not independently checking them. So imagine what we're going to do to test these brakes is we want to see which brake is actually better, but we put all 4 brakes on at the same time. We're testing them all together and we're not independently checking them. And so what we're going to do is we're going to get the car up to 50 miles an hour, hold it at 50 just to make sure it's stable at that speed with, you know, maybe a, whatever that thing is that keeps it at the same speed. What's it called? Cruise control. So we put at cruise control and then after, as soon as we hit this line, we put on the brakes and then we measure them. So imagine we're testing this, person gets it up to 50, puts on the brakes the first time and says that's for brake pad number 1, just because 1's first on the list, and says, oh, we stopped at 199 feet. Like, okay, the person gets in the same car, it's set up the same way, they smoke a cigarette or something, get in the car, 50 miles an hour, put on the brakes, that stops at 201. Oh, that's for brake pad number 2, just because it's the second in the row. The car set up the exact same way. They go here, they put on the brakes, it stops at 198, and that's for brake pad 3. Oh, wait a minute, brake pad 3 seems to be the best so far. They get in the car, it's set up the same way, and they put on the brakes and it stops at 202 feet. Oh, and that's for brake pad number 4. And then imagine somebody says, hey, brake pad number 3 is the best. We can see that difference. And you're like, no, because you didn't independently check them. You had overlap there. This doesn't work. And so this car should stop at the same distance every time. Should stop at the same distance every time, right? The reason why it doesn't is because some type of error. It's either systematic error within the braking system in this case, or just random error. And so we need to make sure that we don't have error in our system as we're checking these. We need to make sure that we don't have a lot of error in here, that we don't have dependencies. What could a dependency be? Where sometimes you go to a machine where you are checking some tissue and you put it on there and you run something, you don't completely clean the machine and you put another tissue and you get like wrong results. That happens all the time in the hospital, right? Where they're like, oh my God, we got to run this again. And they figure it out, no, the first tests were wrong. Okay, so we need to make sure that we're independently checking them, that we don't have any dependency in here. We don't have any issues in here, because if we did, we'd have a lot of error in there. So how do we get rid of, so when we have dependency is caused by, or sorry, as a result of dependency, we have a lot of error, or error could be the cause of it. So when we have dependency, error goes along with it. And so when we have problems with error, we have to be careful with that. So these numbers right here, if somebody were to add them all up and divide and say, hey, the standard deviation was roughly about 200 feet and the mean was this, and you know, or the standard deviation was 1 foot, mean was 200 feet, and they were to start getting calculations from this, all those calculations would be wrong. Right? So if you try to do calculations off of something with the error, it's wrong. And so what we're gonna apply this to, not only with ANOVA, but in regression, we're gonna find out if something is too dependent, we're gonna have issues with error. And the issues we're gonna have with error in our regression is gonna be our standard error. And the way we're gonna measure this in regression is gonna be Durbin-Watson. That's gonna measure to see how much dependency we have. In ANOVA, we just need a random sample. A random sample, okay? So our assumptions for ANOVA is I-N-E, for regression is L-I-N-E. We just add one more. So we need independence, normality, and equal variances. So as long as we have a random sample, we're okay. If it's not a random sample, then we have issues.
Is there a measure of dependency in ANOVA that we can check?
Just a random sample.
What do you mean by random sample?
So you wouldn't go to the same place for the sample,
Yeah.
meaning that,
So you'd have to look at the data and how it's sourced.
yeah, how the data is sourced. And so if you're in a hospital, you'd probably randomly sample. Like if you had 200 people, you just randomly take 40 or 50.
Not mitigates the dependency.
Mhm. Yeah. So randomly sample.
And they're not looking at the Durbin-Watson there.
We don't have the Durbin-Watson for this test. Yeah. It'd be great if they did, but the Durbin-Watson was created much later than this. And just like this was created much later than the t-test. But the the regression uses ANOVA. So somebody's like, hey, wait a minute, we can use this for something else, but in order to use it, we're going to use the Durbin-Watson instead of a random sample. So it's just building. Go ahead.
After dependency, make sure there's no dependency, then we move on to 2D Kramer.
So independence, normality, and the last one's equal variances.
Independence.
So equal variances, what we want to find out is that,
Real quick, so you said with ANOVA, to see if it's dependent, or like independent, it needs to be a random sample.
Mhm.
But with regression, we look at the Durbin-Watson.
that's it.
Okay, and what does the Durbin-Watson need to be?
Let's wait till we get to the Durbin-Watson actually measures something called autocorrelation, which is also dependency. And it's dependency and data taken over time. So it's measuring dependency.
Okay.
Okay. So the next thing we need to measure is when we say one is like significantly lower than the rest, is it always lower? Or are there issues with that? Meaning, is it stable lower? Right? And so what does that mean? And that's what our equal variances is. So our equal variances, we're going to look at our standard deviations, and we're going to have something called the 2 times rule. And what that means is that our lowest standard deviation and our highest can't be double the value apart. What does that actually mean, and why is it a big deal? So imagine we're looking at patients, group of patients 1 and group of patients 2. And when we're looking at group of patients 1, we have the average stay is 1 day, and group 2, the average stay is, I don't know, 4 days. Okay. And imagine if this has a standard deviation of 6 days, and this has a standard deviation of 1 day. Right? But this is lower, but they have a standard deviation of 6 days. This is higher, but it has a standard deviation of 1 day. And we would say, okay, in group 2, they would stay anywhere from 4 plus 1 is 5. 4 minus 1 is 3. They'd say anywhere from 3 to 5 days. On this one, right, 6-day standard deviation, they stay anywhere from 7 days to what? A negative 5 days. But what we would look at is that sometimes this group stays less time than this group. And because that standard deviation is much higher, this one's not always less. And so if we were able to say like, hey, this group is less than this group, we would say, okay, but because of the standard deviation, not always, because the standard deviation is high. Now, if this had a standard deviation of 3 and this one had 6, we're okay. Right? 2 times rule. 2 times rule. So far, so good?
So what if we catch information that, or a variable that has, it's not major 2 times, like the standard deviation is 2 times.
Then you would say it doesn't always do that.
Okay.
So here's what the issue would be. Like, imagine if I'm just going to stick with the same example because I don't want to jump all over the place. So imagine if we're sticking with the same example and we say like, hey, typically this happens, but quite a bit, it doesn't, not always. Sometimes just, right? So if we give the person this respiration treatment, a respirator or something, it doesn't always heal faster, right? This treatment right here, where we give them nothing, seems to heal them just as fast as them going on a respirator, sometimes. And then they'd say, well, so we shouldn't always use this. Because if it's every time, you would say, okay, this is a protocol. But if it's sometimes, then you kind of think like, okay, well, wait a minute, should we always use it? If it's not every time, it kind of throws that doubt in there. That's what the issue is, because you want to make sure that it's less every time, that standard deviation is, or sorry, that mean is pretty stable, right? And if it's all over the place, and it means like, no, it's not real stable. Yes.
So I'm just a little bit confused how to apply the standard deviation to the highest and lowest.
Okay.
So are you just using the standard deviation and saying that, yeah, like I'm just confused. Like,
Okay. So if you have 6 samples here,
yeah.
and one standard deviation is 5, another one is 4, another one is 7, another one is 9. If the lowest is
What
4,
means the samples when you say
So,
5, 4,
no, the standard deviations.
Okay.
So if you have a standard deviation of 4 and you have a standard deviation of 9, we got a problem. So the lowest standard deviation within that mix and the highest standard deviation cannot be more than double apart,
Oh.
2 times the value. But the only one way around that is if your sample sizes in both groups are the exact same, then you don't check the standard deviation, the 2 times rule. And that's the reason why they try to keep groups the same and over 30.
The 2 groups is in like the lowest standard deviation and the highest standard deviation, like say their like count is like both like 15.
That's it.
Okay, or like do all of the,
So if you have 6 groups, the count or the amount of patients in all 6 groups have to be the exact same. So if they're all at like 7 or 8, or if they're all at 10, all of them have to be at 10. If most of them are at 10 and one of them's at 9, doesn't work.
So use the equal variance is 2D, right?
Now, the equal variances is a standard deviation. You need to make sure that the lowest and the highest standard deviation are double the value apart. So what we're looking at is the assumptions here to make sure that the our ANOVA is accurate.
So we're checking INE,
Yep.
independence, which is the original ANOVA test, right? Which tells us if something, if there's a variable in the test that's different. The normality, right? Which is skewness and kurtosis, and making sure that the data is normal. And then you check equal variances, which is the standard deviation.
To make sure that one mean is constantly higher than another one or constantly different, either higher or lower, right? We want to make sure that it's stable. But the first one, independence, measures to make sure that we're not double counting stuff or we don't have issues with that, right? That things don't overlap too much is what we're looking at. And so we need a random sample for that. So
So
make sure
Professor-
that,
But the equal
That's-
variance is the lowest standard deviation going to be 2 times. Well, if you multiply this lowest standard deviation by 2, will that be the highest?
that's it.
Okay.
That's exactly it.
It's equal, or it's like exact.
Yep. So it's double the value of the lowest standard deviation. The highest can't be more than double the value of the lowest standard deviation.
Professor.
That's why we call it the 2 times rule.
But Professor,
Sure, bring it.
but so if it is 2 times more, what can we conclude from that?
So
Like,
if it's
can we
more than,
proceed on-
okay, go ahead.
can we proceed like with looking at other things, or would that mean like we can't, like the data isn't inaccurate, or like what can we do
Okay.
then?
So great question. So if the variability is more than 2 times the value, then what we would say is that whatever means that we're comparing, that one of them is not always higher than another one or lower. We would, so even though it appears to be different, it's not always different. We got some issues with that. It's not continuously different or stable being different. Sometimes it's different, other times it's not, is what we're saying. Sometimes it works, other times it doesn't work. That's what we'd be saying in this case. Not all the time it works.
But
Not
what
all the
would that
time.
mean? What would that mean for our case, for like the
Um,
state?
So if we were looking at patients here and we were saying that, okay, the people that got antibiotics first and they were put on a respirator and they were put in on breathing machines and they were isolated, and we would say that it appears that they heal quicker. And then we look at the standard deviation, we're like, not always. Now, there's a lot of people that we don't do anything and they heal just as quick or sometimes quicker.
Mhm.
Then we'd have to like question like, hey, our process doesn't always work better. And that's what we'd be saying. And so it would kind of throw some doubt on how stable or how continuous that our system actually worked.
But how would we know which one is better?
Yeah, like which one's better? Like we say, it appears to work, but not always, right? And then, you know, if you're a doctor and you have to worry about getting like sued for malpractice, you'd have to say like, you know, you need to sign these documents if we're going to do this, because this doesn't always work.
Okay.
Sorry, quick question. Is it being recorded?
It is.
Okay, is it gonna be on Lima?
So I'm probably going to put it on YouTube
Okay.
as opposed to La Lima, because just in case somebody says something, I'll put it on my YouTube channel and say it was there for a while, call them a damn liar, and then have to delete it if I have to. But that way you guys can see it.
Is that gonna be like sent out to us or?
I'll put it, as soon as we finish, I have to, what do they call it? Where it fixes a video, renders it, and then I'll put it up.
Okay.
I'll link it to, yes.
Really struggling when we use 2D Kramer. It's just after the INE.
So now that we know that this test is okay, now we want to find out which one's different. Okay. Now that we found out that one of them's different, which one? That's a Tukey-Kramer. So now we can look at the Tukey-Kramer, yes.
Sorry, just go back to the assumptions really quick. For checking the independence, we're just checking that it's a random sample. And like I see that like on the exam that we went over, it just says like in the like directions, like using a random data.
That's
like,
it.
blah, blah, blah. So like, as long as we see that, like there's no like numerical anything that we have to check exactly.
It's true.
Okay, we just see it. It'll
Yep.
like say. this
We're
is-
gonna write this up in a second. And the
Yeah.
reason why I'm going through this, and we're gonna write this up in a second, because this is gonna be on one of your tests.
Mhm.
And that's why I'm going through this in detail.
Also,
So as I'm
also-
talking through this, we're actually studying for the final at the same time, not just covering and burning time. And that's the reason why I'm spending a lot of time on this. We're gonna write this up in probably 10 minutes.
Professor, so we check the independence, right? And normality and equal variances.
That's it.
So what if one of those is not right?
Okay, so good question. So if it's not a random sample, then that tells us that all the data is caused by error. Could be caused by error. So it's no go. Right, if it's not random. If it's not normal, then that tells us that our p-value is inaccurate. Okay. If our double, if it's more than double, it tells us that some of the means aren't always lower or higher than the other ones, not consistency. We don't have a lot of consistency there, is what it's telling us. Right? And so are there ways around all of these? So with the random sample, you're pretty much screwed. It's a non-probability sample if it's not random. That's a game ender. Looking at normality, if skewness and kurtosis is not between -1 to 1, it tells us that our probability is off. Now, if our p-value is low enough, we can still reject our null hypothesis. Or if our sample size is above 30, our central limit theorem tells us that we're still okay. Okay. So far, so good. Equal variances. If our data is not equally variable, it tells us that one is not always higher or lower than the other one. And so that kind of sheds some doubt on how consistent these differences are. Did that make sense?
Yeah.
Hello?
Yes.
Okay. You had a question.
It's fine. We can just continue.
Okay. So now that we've tested that, now what we can do is we can look at our Tukey-Kramer to find out which one's different. All we did now was we had a p-value below the level of significance. We reject the null, say one of them's different. Then we want to check to make sure that this test is accurate. Hey, wait a minute. Is it always different, the one that you're saying? Okay, well, let's check our equal variances. Is the probability accurate in this test? Oh, let's check our data to make sure that the probability is accurate. Hey, wait a minute. Is this sample even random? Or is there a lot of error in this sample? Oh, it's a random test. Okay, so now the test is okay. Now we can go to see which one's different. Now that we've established that the test is credible, now let's see which one's different. So then we get into something that's called the Tukey-Kramer. The Tukey-Kramer is going to tell us which one's different. On the Tukey-Kramer test, or Tukey-Kramer, it's known as pairwise. So if we have a couple different samples, if we have 1, 2, 3, and 4 different means that we're measuring, on those, it'll tell us what average each one of the means are. And if one of those is like, 8 days, another one is 9 days, another one is like 6 days, and we have one that's 1 day, and those are our they call it average, and that's means. So we're now going to compare these averages against each other to see if one's statistically significantly different than the rest. But what we're doing literally is doing this. But what we're going to do is we're going to literally do a t-test to see is one significantly different than the rest. So we're going to measure them against each other. So we have one here that's in, so imagine this is 2 and that's 10. We have one in there in 6, one in 9 days, one in 8 days, 9, 8, 6, and one that's out here in 1 day. So we're going to compare. So what I'm going to do is I'm going to write them in what I'm going to call a number line, and I'm going to go the lowest. So the lowest is 9. Sorry, the lowest is 4 with 1 day, followed by 6, followed by 1, followed by 2, because 2 is the highest amount of days. Okay, so I have those in order like that. And what my Tukey Kramer is going to tell me is when I'm going to compare them, it's going to say 4 is different than 3, 4 is different than 1, and 4 is different than 2. I'll be okay, so that is statistically significantly different. And if I look at them, I say like, hey, wait a minute, 3 and 1 are the same, and 2 and 1 are the same. Those are literally the same. These are the same. That's different. If we notice, they're in the confidence interval, and anything in the confidence interval is considered the same. Right? And that's what the Tukey Kramer allows us to see, which one of them's different. Now, if we had one of them in here instead of 9, if it was 11, then it would be out here. Imagine 2 was 11 instead of 9. Then perhaps this one, perhaps it would be 4, 3, 1, 2, and we'd say 4 is different than 3, but 3 and 2 are the same, but 2 is different than 1. So then we would say that group 2 has significantly more days in the hospital than the other 2. Those are the same. This one is more, this one is less. We may find out that, you know, if we put people on respirators, they actually get like hooked on the respirators and they stay longer. I don't know. I'm just throwing that out there. So I'm not at all trying to tell you about what's
I have a
best
question.
treatment. Yes.
How do you know that they're the same?
Okay, good question. So what happens essentially is a Tukey Kramer is literally a t-test. And so with the t-test, what we're doing, and that's why we do the t-test for the regression, is what we would do is we would compare 4 and 3. And we're like, so the mean of 4 and 3, they're the same. And the mean of 4 and 3, they're not the same. And that's what it's doing. And so if it's measuring the p-value against a level of significance, because it's creating a confidence interval and then a p-value, and then for the p-value, it would then either reject the null or not. And if it doesn't reject the null, then they're the same. If it rejects as a null, then they're different. And this is exactly what we do in the regression, is we're measuring each one of those slopes to see if they're different because we're doing an ANOVA. I hope I didn't confuse you by saying that. Did I, or did it straighten stuff out?
Well, I just want to.
No,
see
still kind of confused.
A little bit
Okay.
differently if you, so using the Tukey Kramer, you're comparing the means against each other using the critical range, right?
The critical range, yes.
So
Yes.
the critical range is between 2 and 10. Or
Yeah, depending on what, yeah.
whatever is outside of that is significantly different.
Yes. So with the Tukey Kramer, even though it's essentially running a t-test, what we're doing is we're looking at a critical range instead of it going through all this p-value and all the rest of that stuff, right?
So
Because it is looking at the probability values and stuff. But what the Tukey Kramer is looking at is a critical range. And so it would say if anything is below 2, then it's different. And so then it would look at these two and compare them and say, okay, are these the same? And if that critical value is anything below 2 is different, below 2, anything below 2 is different, then it's going to compare 3 against 4. And it says that, okay, wait a minute, 4 is below that critical value. So it's different than the other one. So it's going to show the difference of the ranges of the values that it has to be different than. And so by comparing the two, we can tell if they are the same or if they're statistically significantly different. And what this plays into is just because a number is higher or lower than another number doesn't mean that it's different. Like when we're looking at these and we're looking at the difference between 8 and 10 or 6 and 10, right? Are those numbers different just because one's higher or lower? So it establishes what is a critical value for it to be different.
And does it give us a critical value?
It does on the Tukey-Kramer, yeah.
Yeah, so when you say different, like when even when we're doing like the hypothesis, not like, oh, one of the names is different, it just means significantly different.
Significantly different, statistically significantly different. And the reason why I say different is because I try to establish that anything in here is the same. So anything that's different from the same is different.
If it's within the range, then it all kind of comes the same.
Yes, if it's within the same confidence interval, it's the same. And so what's that value that has to make it different? So when we're looking at it from a confidence interval, we would be able to say, okay, what's that critical value that it would have to be different than? Right? If we're looking at it from this. And so when we run the ANOVA, we're going to notice that it does have critical values in there too, but we use the p-value. Right? The ANOVA has that F value and the critical value. The F and the critical. Did
Professor,
that help or still stuck?
That helped. Thank you.
Yeah, are you sure or no?
I'm sure.
Okay, I just want to make sure that we're all
So
on the
does it
same
give us
page.
a critical value? Is it a range?
We'll take a look at it in a minute because we're going to write one up. Right now, I just want to cover the theoretical, and then we're going to take a look at an ANOVA and we're going to write it up.
Professor,
Yes.
why do we need to use the t-test if the p-value can already tell us if something is different or the same?
So the p-value just tells us all the data together. It doesn't tell us individually. It tells us, so when we write up our hypothesis for the ANOVA, it says that all of them are the same and our alternative says one's different. So when we reject our null, all we're saying is one's different. The Tukey-Kramer tells us which one.
Wait, so the t-test tells us that
Well,
one.
so the Tukey-Kramer is essentially running something similar to a t-test is what it's doing, and it's creating critical values. So what we're going to do is after we know that one of them is different, because you said the p-value tells us which one's different. So the p-value in the ANOVA only tells us one different. It doesn't tell us which one is different. In order to find out which one, we need to look at our Tukey-Kramer. And with the Tukey-Kramer, it's going to give us certain values on it. And it'll tell us which one's different using the Tukey-Kramer.
What if we look at the t-test? What does the t-test tell us?
So we're not going to run the t-test for this. So with us, we use a Tukey-Kramer because it's probably the one that is used most of the time.
So they don't even use t-test?
No, we're not going to run a t-test. But in our regression, instead of running a Tukey-Kramer, we're going to run a t-test to see which ones are slopes. That's the only reason why I mentioned t-test, because I wanted to link them together for later on, where we can start looking at that.
So Tukey-Kramer is just a bunch of t-tests from
Essentially,
seeing where
just to see if one of them is statistically significantly different than the rest. That's it. Does that make sense to you?
Yeah.
And so other people, and the reason why I say it like that is because there's more tests than there's a Tukey-Kramer. The marketing department here is going to use one called the Duncan. It's based off of the same principle. And once you learn how to read the Tukey-Kramer, you can read the Duncan. And that's the reason why I kind of just like to talk about it like in general and not get too specific. That way, when you get to your marketing class, your professors are going to say, no, everybody, well, they like the Duncan, but for the most part, I'd say a good 90%, more than 90% of the people use the Tukey-Kramer. That is the standard. That is the standard. Okay, so far so good. Now let's take a look at one of these and let's write it up.
I have one question, please.
Sure, bring it.
For the Tukey-Kramer, are you looking at the p-values or the means?
So with the Tukey-Kramer, what we're trying to do is we are comparing the means, or what they call the averages. And so we're comparing the means against each other to see if one mean is statistically significantly different than another one. Right, in each group, because we have multiple different groups and we're trying to test to see which group is significantly different, is essentially what we're trying to do. And then now what we're going to do is we're going to actually look at an ANOVA. And we're going to look at how to interpret it and how to write it up. And this is 25 points out of the final. And that's the reason why I've been spending a lot of time in it. And it's also key to understanding regression. Okay. So there's a kind of a method to my madness. Sorry, I'm downloading this this file, and I'm also downloading the template of how to write it up. And so if you guys want, you can go to the tortilla file, go to Excel note files. You can also, after you go to Excel note files, you go to chapter 10 and go to C sample tests means, and you can go to the tortilla file. And then what I'm going to do is we are going to look at how to write up the hypothesis document. And we're going to write this up because I want to help you guys to be able to understand it, write it up, and what does it actually mean. Okay.
I'm sorry, how do you get there again?
So go to resources. And let me share my screen. Screen share. Lima. So go to resources. After you go to resources, I want you to go to Excel note files. Chapter 10 and C sample tests, and then the tortilla file. Okay, so now, oops. It's not sharing because it didn't show me sharing. Tortilla file. Can you see this, Tim?
Yes.
Okay. So we're not going to call this tortillas. What we're going to say is this is treatment A, B, C, and D. Okay. We're going to just stay with the same theme. So this is treatment for people that come into the hospital for COVID. One of them, A, is, I'm going to say A is we do nothing. They just come in, we put them, give them a bed. We just, make sure that they're clean, wipe their head with cold water and feed them. Right. So A is kind of, oh, we're not really doing a lot for them. B, perhaps we look at that and we're like, okay, so with B, we're going to give them like some antibiotics. Okay. And so with C, we're going to give them antibiotics, and we're going to also do some breathing treatments. And with D, we'll give them breathing treatments. Okay. But A, we're just, they come in, we just, wipe their forehead, keep them clean, feed them, and kind of just watch them. We're not really doing a lot of stuff to try to help them. And we're going to compare and say, hey, well, which one of these groups of people, and so we have groups in each one of these, not for patients, but we have 30 in each and every one of these groups, right? And so as we're measuring them, we like to write it up, and we're like group 1, 2, 3, and 4. They'll all heal about the same and get out of the hospital about the same time. Our alternative is at least, and this is the average time that they stay in the hospital, at least one of these groups the average stay will not be equal. They'll get out a little bit sooner or significantly sooner. One of these treatment things will work. That's our hypothesis. So when we look over here at our summary, we see our groups. These are how many people are in each group. A, 6 people, they got really no treatment. B, 6 people got antibiotics. C, 6 people got antibiotics and breathing treatments. And D, 6 people just got breathing treatments. We want to see which one's going to work the best. These are the sum of all the days that they've stayed. And when we divide that by 6, it gives us an average. So group A on average stayed 95 days. Group B stayed 84 days. Group C stayed 75 days. And group D stayed 81 days. And that's what our data is showing us. It's giving us the averages. And so we're comparing each one of these averages. Each one of these is amount of days. So group 1 mean, they stayed 95 days. Group 2, they stayed 84 days. Group 3, they stayed 75 days. And group 4, 81 days. That's what each one of those are, is those groups, and they represent how much time they stayed. And we're saying at least one of them is different. And with ANOVA, it either can be different on the upper, they stayed more, or different on the lower. Right? And that's why I wanted to stay with just the upper and lower, the two-tailed test, just so it would be easier transition to ANOVA. Okay, that's what we're looking at. And so how do we know if one of these treatments is actually statistically significantly different? So we ran the ANOVA, and when we ran the ANOVA, we look at where it shows differences between groups. So within each group, some people stayed less and more. We understand that. And then we also want to see the differences between groups, because some people will heal quicker. We understand that there's variabilities, and that's what that's showing us, the difference between groups and the difference, within groups. And those are those numbers right there. That's sum of squares. I'm going to go back here, which is just a little bit over an hour ago. And I'm going to take a look at how the sum of squares is. Remember we did that? The sum of squares is just simply where we square this data and we're kind of adding it all together. That's what that is. Sum of squares, SS. Degree of freedom, what is that? Well, how many groups do we have? We got 4. We remove 1. Our degree of freedom is 3. We did that here. So far, so good. We look over here and we look at the variance. What is that? Square root that, you get your standard deviation. Okay. See that F and that F critical? Remember where you were asking? Somebody was asking like, okay, the critical values and that type of stuff. I said in ANOVA, they have the p-value and they also have critical values. This is the same thing. They're both associated with the same. So what it's telling us is, so F, because it's named after the guy Fisher, right? So F critical, the value has to be higher than 3.09 to be different. Our actually F value is 23, which is higher than that critical value. So anything higher than that tells us that one of them's different. I want to say reject the null, but it's not using, the whole hypothesis idea. No, the p-value does that. This one just tells us one of them's different. Now, the way that we're going, we're using that academic approach. And so with that academic approach, well,
values greater than critical value, something different.
yeah, so critical value tells you anything higher than this, it's different.
Okay.
And the F is telling you what that value is. We're using the p-value. So that p-value right there where it says E07, that E is a scientific notation where it says 0.7, which tells us we're going to move that decimal place 7 places. So instead of 9.9, what it's going to be is we're going to move this 7 places. 1, 2, 3, 4, 5, 6, 7. So we're going to have 6 zeros in front of that 9. So that is going to be a p-value of 1, 2, 3, 4, 5, 6, and then a 9. That's our p-value. A p-value, again, is our probability value. Our level of significance is 0.5. Again, if our p-value is below our level of significance, we can reject our null hypothesis. If it's not, then you don't. If we have a p-value of 20, there's insufficient evidence to reject the null hypothesis. None of these treatments make any difference. If it was 20, but 1 minus the p-value tells us how confident we're in an alternative. So if we had a p-value of 20, we would say there's insufficient evidence to reject the null, but we're 80% confident in the alternative. We need to be more than 95% confident because that's what our confidence interval is. We need to be more than 95% confident. Okay. So in this case, we're looking at this and our p-value is below our level of significance. We ran this at the 0.5 level. So we'd be able to say this. There's significant evidence to reject the null hypothesis that all these treatments are the same. They're not. We are 99.99991% confident that one of them's different. Which one? We don't know. The ANOVA doesn't tell us that, but one of them's different because our p-value is below our level of significance. Now we want to check to make sure that this test is accurate, and then we'll check to see which one's different. Because if the test isn't accurate, why are we saying which one's different? How do we know if our test is reliable? If one of these means is always higher or lower than the other one? How do we know if this p-value is accurate? Because our sample size is less than 30. How do we know if this test just isn't based on a bunch of errors because they're not even cleaning the machines and perhaps these people shouldn't even be released? We need to make sure that we have a random sample. So now we want to check our assumptions just to make sure that this test is legit. So our independence, we need to make sure it's a random sample. Right? We're randomly using different machines to check these results to make sure that they're okay. It's a random sample. Okay. Normality, skewness, and kurtosis. That tells us the accuracy of the p-value because we're using a p-value to reject a null hypothesis. And the last thing we need to check is our equal variances. 2 times rule. We want to make sure that one of these means is either consistently higher or lower than the rest. It's not higher sometimes or lower sometimes. No, it's consistent, that these results are consistently accurate. Okay, and those are our assumptions. So let's look at them. So
how do we know it's a random sample from this?
So it would be on if we were testing this, it would be like in the directions. This is a random sample based on blah, 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 blah. That's the only way of telling, is they would have to state it. Right?
Stated.
Yeah, it would have to be stated in the test. We did a random sample of this and we randomly used different machines. We randomly used different doctors to check it. It's not based on just one doctor's results, one machine's results. We tested them several times on different machines. And so you would have to state it, right?
Okay, but what if you're just like, you would gather the data and look at the data? How
You
would
got to make sure it's random. If it's not random,
What makes
and
it random?
yeah, if it's not random, you got to be careful.
But what
Right.
makes it random?
So again, for this test, you would want to make sure that you are using different machines to measure to see if they have COVID. Right? You don't want to use the same machine that says, oh, no, they're all still sick. Maybe it's the machine is no good. So you'd want to use separate machines and different people to check it, because maybe the person that's checking it is creating issues too. So you want to use different people checking it, different machines, random times, and that way you know that the results are coming from multiple different areas and multiple different sources. And that's how you would do a random for this test. Does that make sense?
Yeah.
Okay. Normality, we're going to check skewness and kurtosis. So here, when we look at skewness and kurtosis, when we look for sample A, our kurtosis is a little bit flat and it's not normal. What this tells me is our p-value is not accurate. When we look at sample B, kurtosis again, flat and not normal. For sample C, it's okay for skewness and kurtosis. For D, it's telling me that it's peaked and it's skewed to the right and not normal. So this tells me that our p-value is not accurate. And again, the worst that this is off is by like 3. So this is off by even less than 1%. This test, the p-value is off by 1%, less than 1%. Okay, that's how inaccurate the p-value is. Sorry?
Where do we see that?
So do you see the skewness and kurtosis?
Yeah.
Okay. And those numbers have to be between -1 to 1.
Yeah. And if they're
And
not,
so now we need to assess, well, a 3, how far is that off by? Right? How far is a 3 off by? And so they have a bunch of these numbers in a bunch of different books, but just as a rule of thumb, you're probably looking at about 7, 8, close to 10 is off by 1%. Skewness or kurtosis. It's kind of a rule of thumb. And so if it's below like a 10 skewness and kurtosis, it's off by 1%. And so when we look at our p-value, so our p-value is 1, 2, 3, 4, 5, 6, and then a 9. Probability value is the p-value, and it's off by less than 1%. Hell, if it's off by 10%, watch this. Has 6 zeros and then a 9, even if it's off by 10%, right?
it's
I get
still,
one to run 0.
it's still different, right?
That's still below 0.5. It's off by 10%. Okay, get rid of a 0. That's still below 0.5. I'm still going to reject the null hypothesis because that's still below 0.5. Okay. Or if our sample size is greater than 30, it's assumed to be normally distributed, right? It's assumed to be normal because of the central limit theorem. But ours isn't, so we need to check it. So I'm going to state that the p-value is not accurate, but the inaccuracies is really not going to affect, because our p-value is so low, really won't affect our decision. Okay. Now, equal variances. I'm going to look at my standard deviations. Now, the lowest standard deviation in this sample is 3.8, and the highest is 4.8. So double the value of 3.8, we're looking at, what, 7.6 or so? That's within 2 times the value. So we can say that when we find out if one of them is higher or lower, it's consistently higher or lower. But also because the sample sizes are the exact same, the counts, we would just assume that it is. It's assumed to be that, just a rule of thumb. So far, so good. So now let's take a look at the Tukey-Kramer. Can you guys see the Tukey-Kramer, Tim?
Yeah.
Okay, so here's the Tukey-Kramer, and this is the one that I was talking about. And so let's take a look at how you can tell the difference between the Tukey-Kramer. Okay, so if you look all the way up on the left side, it shows the means. So it says sample mean. That's like B5 or so. And it shows for group 1, it's about 95 days, group 2, about 84 days, group 3, 75 days, group 4, 81 days. And so we see those groups. And so when we make our number line, what I like to do is to have the lowest and then go to the highest, right? And so the lowest number in here is 75 days. So that is group 3. And if we look at the board over there, we see the lines where it has 3, 4, 2, 1. If you look at the board right here, if you look at the Excel spreadsheet, the number line is already there for you. So the lowest one is 3, followed by 4, followed by 2, followed by 1. Okay. So we look at 3 versus 4, right? 3 versus 4. And when we look at group 3 to 4, that's the last one on the very bottom. It says group to 3 or 4. That would be like E10, I believe. It says group 3 to 4. It's comparing those two. It's saying what the absolute difference between those two groups on the amount of days that they stayed is like 6.5. But the critical range, H, is telling us, oh, it has to be more than 6.8 days, and it's not. And if we look at those, and we're looking at 3 and 4, one is 75, the other one is 81 days, it's not enough of a difference. They're literally significantly the same. So those two treatments, they're the same. We notice that it's a few days more or less, right? The difference between 75 and 81, roughly, you know, few days more, but not enough to be significantly different. And then when we look at group 4 and group 2, that's the next one on the bottom, that's probably E9, group 2 and group 4, and we go all the way over to I, and it says means are not different. Group 2 and group 4, they're the same. We circle those. Do we see they're circled right there? On K18 or 17, somewhere around there, they're circled. Those are the same. But how about group 2 and group 3? Group 2 and 3 are different. So group 2, here's a, it's okay. But I had that extra, this right here, but before you put it on, you got to measure them, you got to drill it. Otherwise, if you glue it down, there's no way you're gonna be able to drill it.
Okay,
To
cool.
put
And
the
then
strings.
This is for concert. Or what?
I think it's concert, yeah.
Okay, cool. Appreciate it.
All right,
I'll see you Tuesday.
all right. So group 2 and group 3 are different. If we look at them in here, they're different. 2 is different than 3, but 2 is the same as 4. And how about group 1? Group 1 is different than group 2. Group 1 is different than group 4. And group 1 is different than group 3. So group 1 actually has the longest days, and that one is significantly higher than the rest. And so we'd be able to say that, you know, 3 is definitely different than 2. 3 is definitely different than group 1, but it's not significantly different than group 4. And we're looking at the least amount of days that it stayed. So we can say we do see some stuff there that is different than a couple of them. It's 3 is different definitely than 2 and 1. But it's not really different than 4, but 1 is different than all of them. And we look at it and say, oh, that's the one that we don't give people treatment for. They stay longer.
So the 3 and 4 would be the best treatments to like take.
Probably.
Okay.
3 would probably be the best treatments because it's a less days, is what
Yeah,
I would
but
say.
4 is like same as 3. So
4 is the same as 3, but it's really the same as 2 as well.
okay.
but 3 has the most difference from all the rest, right? And so treatment 3 is where we gave them breathing treatments and antibiotics, and treatment 4 is just kind of breathing treatments, right? So we would say probably 3 is better, right? But it's not always lower is what the key is. That's what this is saying. It's not always lower than 4, right? But it's definitely lower than 2 and it's definitely lower than 1.
So how do you like, when you look at the Excel, how do you know like what numbers pair up, like the 3 and 4? Do you look at like the sample mean?
Oh, so see that, so look at E and go down to like E4 and see where it says comparison.
Yeah.
And you look at, it's comparing group 1 and group 2. And then if you go all the way over to the right where it says I, that says the results. Are they different or are they the same? And those results are based off of the critical range on H. So that critical range means that it's got to be higher than that to be different. The critical range, and then what the absolute difference is. So one of them's giving you the critical range of what it has to be higher than, and the other one's telling you what that difference is. So it says if it's higher than 6.8, it's different. And you look at what the difference is, and it's 10, which is higher than 6.8, which is telling us, no, this one's different.
Okay.
Do we?
Kind of looks like that on the final. And like what we have the critical range.
Yeah, but you can just look at means are different. You won't need to see that, right? It kind of, it interprets it for you, but I'm just telling you where that difference is coming from. So you just look at it and it says group 1 and 2, means are different. Group 1 and 3, means are different. Group 1 and 4, means are different. Group 2 and 3, means are different. Group 2 and 4, means are not different. Group 3 and 4, means are not different. That's what it's telling you, right? And that's why I use a number line so you can visualize it. So now let's write this up and cover, 25%, more than 25% of the final, okay? So I'm going to also launch our, on that how to write up doc here. So I'm gonna see if I can minimize that. Make it a little bit smaller. Like I said, we're gonna write up something in the final. Hypothesis write up. Okay, I'm gonna drag this over to the side. Can you see the hypothesis write up doc, Tim?
Yeah.
Okay, good. I know with PC, sometimes you can't do that. I know with Mac, you can. Move you guys out of the way. Okay, so I'm going to use ANOVA because this is an ANOVA, right? And so here, my hypothesis is showing the means. I have 1, 2, 3 means. I want to equals. Just copy that.
Wait, Chris,
Yes.
I don't know if I'm the only one, but I can't see the dog.
Yeah, actually, I
Yeah, I can't see it either.
Oh, okay. Sorry. I thought when he said he could.
I
That,
thought it was the same. I thought it was like still on the
okay.
30.
Sorry about that. Let me do that again. Sorry, I thought when I asked him that it was, oops,
Yeah, that's my bad.
that's okay. Don't worry. Can you guys see both sides or only one?
Only one.
Okay, yeah, it's PC. That's why I always have people use a Mac, because with the PC, you can't split the screen. It stinks. Okay, so which one do you see? The ANOVA write up or the Excel?
The ANOVA.
Okay, all right. So I can see both sides of my screen. I'm sorry, you guys can't see both sides. It's the PC and it does that. It won't allow the dual sharing. I don't know why. But it just is. So I apologize. So I'm going to write my hypothesis, and my null is that sample 1, 2, and 3, and 4, all the treatments are the same. Not all means are equal. Okay. And then I'm going to, who has a Mac? Do you want to share it? That way we can do both of them.
Yeah, I can do.
Okay, let's do it. I'm going to stop sharing mine. That way we can do it and you guys can see where the data is coming from.
Hold on.
Okay.
It's
think I have-
basically the document that we've been using all along, right?
Yeah, that's it. That's it. I'm hoping this is useful because like I said, it's 25% of the final. And then we're right after this, we're going to go to a chi-square. And that will be like more than 50, that's probably 30%, right? And we'll go to the other one and that will be like, 50 out of 90 points. Right? And then we'll cover some of the other stuff, the regression after. So you can bring it anytime.
Yeah, sorry. My bad.
It's okay. So what I'm going to do is I'm going to